Power series. In this session, I will introduce the power series, and I will focus only on interval of convergence and interval of convergence of the power series. Okay, let's check. The power series is the series in which each term is a power function of the form C sub n x sub n. As we can see, we have the summation C sub n x sub n. C sub n is a constant coefficient, is a coefficient of the series. C sub n will depend on n, usually depends on n, and will change respectively to n. X is a variable. And so we do have a power functions, like the addition of the power functions, or we can say theoretically, we can say it's a polynomial with infinitely many terms. What is important part? Important part is to find the value of x, like for what variables, for what x will this power series converge? That's our plan for this session. Okay, that's as we just mentioned, the power series may converge for some values of x or may diverge for some values of x. And we may call power series a function, but only if the domain of the function is the set of x that will allow the convergence. And we will call domain of the power series, we will call an interval of convergence. That means set of x that will give us convergence. And with this set of x, with that domain, we can call, yes, this is a power function with infinitely many terms. But we can only consider this as a function if it is convergent. Okay, for instance, let's just start with the simple and something actually familiar formula. Let's consider that the coefficient C sub n is a constant, it's just 1. C sub n is 1 for all n's, and then what we have? We do have 1 x to the power of n. Looking at the expanded form, we have x to the power of 0, 1, x to the power of 1, x to the power of 2, and so on. That's when we may notice that in order to get another term, we multiplying by x. That means x, in this situation, x is a common ratio. And that's actually the geometric. That means common ratio, the notation from the geometric series previously, not from the power series, is x in this situation. That's we may have this power series, and we can call, this is like, a function, but we may only consider the intervals where this power series is convergent. And we remember from the geometric properties that if the common ratio is between -1 and 1, or actually equivalent notation is absolute value of the common ratio must be less than 1, that's the same thing, then this geometric series, this power series in this situation is convergent. Converges, that means that's important. Let me put this x to the power of n, then 1 plus x to the power of 1, to the power of 2, to the power of 3, and so on. What I would like to say, if we only consider x's from that interval, we may have the sum. And we also remember for the convergent geometric series, the sum was equals to the a minus 1, a over 1 minus a common ratio. A is a first term, that means the first term is 1 minus and common ratio is x. And that means this will be quite important tool in a minute. Okay, because this power series has this representation, or maybe I suppose to say the other way. I can consider this as a function. Like, let's say this is just the rational function, 1 over 1 minus x, quite simple. But this rational function has a power series representation. Yes, we may approximate this rational function by this polynomial. And depends, maybe second degree, maybe third degree, maybe fourth degree, maybe nth degree. And that means this will be quite good tool. Let's say this way. Okay. Okay. And otherwise, if the x's are outside that interval, the power series diverge, but we're not interested. We're just looking at the convergence. And this will be the interval of convergence. Okay? I can, if I will draw this on the number line, just getting back to the convergence, interval of convergence is just not including -1 and 1. Okay, that means that's interval. And sometimes we will say I, interval of convergence between -1 and 1. Also, we need couple of parameters. Okay, but okay, we know interval of convergence. I was gonna say what is also important. Important is a center of this interval. And it's not challenge. The center is 0. Let's call it A. A will be the center. Okay, and let's maybe do one more thing. As soon as we have a center is the center. We have the same distance to both edges, like to the left and the right-hand side. That means that distance from the center to the left or to the right-hand side, we will call a radius of convergence. And radius of convergence, the distance is 1. Yeah? As we may see later, will be quite helpful as soon as we know center, and we will know the center based on the formula. We don't have to do anything, but let's see. But as soon as we know the center and the radius, we know how far we're going from the center. Most of the cases, the formula will be a little bit more complicated, more complex. That means the additional thing that we have to do, we will also investigate the endpoints. Yes? Center, distance from the center, 1, 1. That means the interval is from -1 to 1. And because this is geometric one, we know that we're not including -1 and 1. But for the more complex one, which are not the geometric one, we will also investigate the endpoints because we may have closed interval, maybe one-sided, maybe both. Okay, we know everything. That means the point for this session is to find an interval of convergence and the radius of convergence. Okay, let's look at the more general form. The more general form of the power series is summation C sub n, and not just x to the power of n, x minus a. And then we have the expanded form, substituting instead of n, 0, 1, 2, and so on. And how we call this? We actually call that this is power series in x minus a. I mean, all of them, 1, 2, 3 statements are equivalent. The power series about A, but I think the middle one is quite popular. The power series centered at A. That means whatever quantity we subtracting from x in this main formula, like x minus a quantity, that will be a center. Okay? And we know right away, that's what I just said a minute ago, looking at the formula, we will know right away the center of the interval. Okay, we will know the center. And then if we figure out the radius, which we have some tools, then we will almost know the interval, which that's important. Interval of convergence is the domain of the function, but function is the power series in polynomial with infinitely many terms. Okay, that means just the notation. And for instance, if I will give you the formula, because C sub n could be any formula, let's say 1 over n and then x minus 2, starting from 1 because it is 1 over n, to the power of n because it's x to the power of n. And we can say right away that the center is 2. Yeah? And then we will do the next things. Or for instance, let's say C sub n is defined as 1 over n squared, or let's say plus 1, because then we will, and then x plus 5 to the power of n. Yeah, this is just the examples. Then we can see that the center is -5 because we're subtracting a -5, x plus 5. And let's make sure that we know how to identify, how to locate a center. Okay, it's me now. And let's look at this because the point is to find this interval of convergence. For instance, yes, when we will look at, this is actually the same thing. This is just the expanded form. The second line is just longer. When we will take the power series, yeah, that's the most general form, yeah, the center is A. And what actually happened? What actually happened if x, the variable x, is equal to exactly to the center, which when x is A, yes, we can see we may substitute. Actually, I suppose to say, let's say x is A. That means this will be A, this will be A, this is A, this is A, then this is 0, 0, 0, 0. Only one term, the first one will stay because it doesn't depend on the variable x. Yeah? That means what happened when x is exactly a center A, then we will always have this summation equals to the finite number, the first term, the constant c sub 0. That's in what we're saying, that even if we're looking for some interval of convergence and we're not getting any x values, we have to always remember, like, okay, this power series is divergent for all of the numbers except the center. That means always at the center, power series is convergent. That means we will always have at least one value of x. That means in this case, we can say that the interval of convergence is just set of one number. That's interval of convergence, okay? Also, let's just say center, what is, yes, center was, center is A, yeah, that's okay. That means this is A, and this is the only number, yes, for the convergence, for the domain. And we may see we're not going anywhere to the left or the right hand side. That means if the interval of convergence is just one number, the center, radius is 0. Yes, because we can see we're not moving. Let me even erase. The radius is 0, and this is still fine. We know if the radius is 0, we will know right away, okay, interval of convergence is just one number, and it must be a center. Okay, I mean, that's some special cases. But now let's solve together 3 exercises, 1, 2, and 3. And each of them will be slightly different. Okay, and you can watch me, but later after the session, I will recommend that you can solve them one more time without my help. Okay, for what values of x is the series n factorial x to the n convergent? Okay, convergent. Okay, that's what we're basically looking for the interval of convergence, or I can say domain. I just typed the question this way. Okay, that's what will be our tool. Our tool most likely will be the ratio test. Okay, because ratio test is quite nice. We remember the ratio test. Because what we do have a formula which represents coefficient c sub n. This is n factorial. And we will always have power form x to the power of n. And as we remember, ratio test is good when we see a couple of different mathematical expressions. Power form, exponential form, factorials. No? That means let's apply the ratio test. Let's see what we will get. We can always start with the ratio test. Limit as n goes to the infinity, a sub n plus 1 all over a sub n, absolute value. Limit as n goes to infinity. Okay, n sub, this is, of course, the entire term is a sub n. That means when we add 1, a sub n plus 1, we will have n plus 1 factorial and x to the power of n plus 1, and then divide by a sub n, n factorial, x to the n. Absolute value. Absolute value is quite important because x could be positive or negative. N is always positive, but the variable x. Okay, we have to simplify. N plus 1 factorial, I can rewrite as n factorial times n plus 1. X to the power of n plus 1 is x to the power of n, x to the power of 1, and this is n factorial x to the power of n. Let's simplify because we like this moment, okay? And then what's left? We do have n plus 1, okay? And we do have x. And for n plus 1, for the n expressions, I don't have to keep absolute value because this is positive. Only like probably you will see me, all of my solutions. At the end, I will kind of isolate n's and the x, the variable. And for the x, I will always keep absolute value. Okay, this limit, yeah, and we're looking at the limit as n approaches infinity. That means everything what is not n, it's constant with respect to the limit. That we can only look at that limit and then we will copy that part. And n plus 1 goes to the infinity. That means the entire limit in big number times any number. X could be 1, 2, 3, any number. It will be infinity. And by the ratio test, we can say that, remember, by the ratio test, when we're getting that limit, if it's infinity, we can say that the series is divergent, diverges. No, yes, no other option. That's we know this is divergent. Okay, for all of the x's is divergent. Yes, for all of the x's. But what we know, this is power series. So we normally will say divergent, yeah? But we may provide one x value that will give us convergence. That's mean always when we will get infinity. Please remember that we have one x value, which is a center that will give us convergence. Okay, because of its infinity, no other x's, but the center, how we can recognize the center, nothing is subtracted from x. Nothing, it's just x to the power of n. That means I can rewrite this, right? This is x minus 0. If nothing is subtracted from x, it's of course 0. That means this is a center. Okay, and now providing an interval of convergence is just a 0, is just one value. For x equals to 0, this power series will converge. And we can even find the sum, okay, n factorial x to the power of n, starting from 0. 0 factorial is 1, x to the power of 0 is 1, and then we will have 1 factorial x to the power of 1, 2 factorial x to the power of 2, 3 factorial x to the power of 3, and so on. But this is convergent on, and it will be convergent to 1. Yeah, this will be equal to 1 if, yes, if x is 0, the center. That means if x is 0, we have a summation 1. Okay? Perfect. Example number 1. And I do have some solution. I type it for you. That's we can see infinity, but only converges if x is 0, center. Okay. Okay. Example number 2. The same question. Find the domain for what values of x this series converge. And now we have the summation from 1 to infinity, x minus 3 to the power of n over n. Okay. And that's we may, yes, for some values of x, we may have convergence. We may notice right away the center is 3. That means I can maybe put this 3, maybe only 3 will be the interval, or maybe in this case, we will go away a couple of values. This will be radius. Let's check. Ratio test. Ratio test. Limit as n goes to the infinity, a sub n plus 1 over a sub n. I know that you are fluent with the ratio test. And it's one of the favorite. X minus 3 to the power of n plus 1 over n plus 1, and divide by a sub n means multiplying by reciprocal. Okay. Actually, it's okay. I can rewrite one more time because I supposed to do this. X minus 3 to the power of n, x minus 3 to the power of 1 times n plus 1, x minus 3 to the power of n. Okay, and what we can cancel out? I think just this, okay? Not bad. Now, n on the top, n plus 1 in the denominator. Yes, n plus 1, and then x minus 3 an absolute value. We remember, we don't have to put absolute value of x. And now we have to compute this limit, n over n plus 1. The limit is 1 times, I can maybe write this, 1 times x, absolute value of x minus 3 is absolute value of x minus 3. That's in this case, by the ratio test, our limit depends on the x, because that's typical. Depends on x. And we know that the answer, yes, by the ratio test, in order for the series to be convergent, the limit must be less than 1. Perfect. We have nice absolute value inequality. Let's solve it. So what we have? We have x minus 3 absolute value less than 1. X minus 3 must be between -1 and 1. That's how we solve absolute value inequalities. And adding 3 to both sides, this will be 4 and this will be 2. Okay, it means the interval, the potential interval, because we still have a couple of steps, is between 2 and 4. And if we will make some arithmetic mistake, algebra mistake, possibly, we can always correct it, because let's put it 2 and 4. We knew the center. Center is definitely right, and this is correct. 3 is between 2 and 4. That's going to be good. I did add the numbers correctly, or subtract. Okay, 2 and 4. It means now an interval is between 2 and 4. However, we still have to test the endpoints, 2 and 4. We know the radius. Radius is okay, because from center, we're just going away 1 unit. One distance, 1. From 3 to 4, from 3 to 2. That means this is definitely, and we have. But this is still not completed. Maybe we can add 2, maybe we can add 4. The one small problem, I mean, easy to fix. We cannot use the ratio test to test the endpoints, because let's see, if I substitute instead of x 2 minus 3, -1. Absolute value of -1, it's 1. By the ratio test, if the limit is 1, the test is inconclusive. The same will happen when we substitute 4, right? 4 minus 3, 1, absolute value of 1, 1. By the ratio test is inconclusive. That's why we cannot really do the ratio test. But since this is we're not testing the entire number line, we're not testing infinitely many numbers, we're just testing 2 values. Let's simply substitute them, 2 and 4, to the original formula, and let's just look at the infinite series. It will be not power series. Do I have extra page? Okay, that's me. Let's take x equals to 2. And this will be the process. Starting from we're starting actually from 1. Okay. So let's see what we're getting. And you also have lots of practice. This is n, this is 3, it's x, right? It's x, but I just wanted to substitute 2. It's x minus 3, I will substitute 2, 2 minus 3 to the power of n over n. Okay, that's what we will do. Let's see what we get. 2 minus 3 is -1, -1 to the n over n. We're getting alternating harmonic, and this alternating harmonic is definitely convergent series. That means the x equals to 2 is giving us convergent. Yeah, and we don't have to say, I know that we got used to by alternating series tests. We don't have to at this point, but we know it's convergent. That's what I will do. 2 is definitely in. Yeah, that means we will include 2. Doesn't affect the radius. Yeah? Doesn't affect the radius. From 2 to 4, let's check about 4. I mean, I will do the same thing, but we will substitute the other endpoints. Okay, that's mean, please remember the endpoints we simply testing like 4 minus 3 to the power of n. Let me put the color for you and let's check what we're getting. We're supposed to get something nice. 4 minus 3 is 1. 1 to the power of any number is 1. 1 over n. Harmonic, divergent. This series is divergent. That means 4 actually will stay open. And we're not including 4 because x equals to 4 is providing divergence. Okay, beautiful standard example. Yes, we did everything. We did the ratio test, we did the inequality. We definitely didn't make the mistake because the center was correct between 2 and 4, and we did test the endpoints. That means the interval of convergence, the set of x is between 2 and 4, including 2, not including 4. And that's the endpoints. Beautiful, beautiful. Okay, and one more example. Oh, this is the solution. Yes, we did it correct. You may pause the video, you may look at the typed solution, but we know that is handwriting is better. Okay, exercise number 3. Find the domain of the Bessel function defined like this. Okay, that's me. Don't worry. I just say yes, Bessel function, because it is quite important function. Later, maybe at some application of engineering, we have lots of engineering and software engineering students in the classroom. But this is, basically I just choose this example because it's interesting and it is a power series. I know it looks crazy, but let's see, summation from 0 to infinity, -1 to the n, okay, it's alternating 2 to the 2n, n factorial squared, and x to the power of 2n. It's okay, but we do have the variable x to the power of 2n. We may notice nothing is subtracted from x. That means center is 0, 0, center is 0. Okay, let's do the same thing. Finding the domain means looking for the interval of convergence. Let's apply ratio test. Limit as n goes to the infinity of a sub n plus 1 all over a sub n absolute value. I hope we can manage this. Okay, -1 to the n, absolute value will remove this. That means that's not a variable. I can ignore this. Then maybe my writing will be a little bit shorter. X to the power of 2n. That's been x to the power of 2 and n plus 1. Let's actually say 4 to the n. Okay, that's the same thing. 4 to the n plus 1 and n plus 1 factorial and actually squared. Now, dividing by a sub n, I will multiply by the reciprocal. 4 to the n factorial squared and x to the power of 2n. -1 to the n is removed because it will become positive. Okay, this one, of course, we have to distribute 2n plus 2. X to the power of 2n, x to the power of 2. 4 to the n factorial, n factorial. 4 to the n times 4. N plus 1 factorial, I can rewrite as n factorial times n plus 1. And it's squared, I can repeat. N factorial, n plus 1. And x to the power of x squared to the power of n. Okay, this is gone. Factorials are gone. 4 to the n, gone. Wow, so nice. Let's see what's left. No n on the top, then I can put 1. 4, and then we have n plus 1, n plus 1, n plus 1 squared. And 4 and x squared. That means I can put times x squared. And I suppose to keep absolute value, but we don't even have to keep absolute value because it's x squared. That means always positive, but let's keep it. Okay, and that's when you know that form. It's easy to compute the limit. We have to compute the limit of this because this is constant. I will just copy this. And 1 over n squared, 1 over 4n squared, this limit is 0. And 0 times anything, it will be 0. 0 is always less than 1. By the ratio test, this power series is convergent for all of the numbers. Convergent for all x's, all real x's. And that's the beauty of this power series, which is called, yes, Bessel function. We have lots of application, but we can see that convergent for all x's. We can say an interval of convergence is from negative infinity to positive infinity. Can maybe a little bit, which we can see a little bit different. This is x. And even makes sense, this is 0. That means interval is all of the numbers. Actually, what I was gonna to ask, what is the radius? What will be the radius? I know that you answering in your head, you answering aloud. The radius is actually infinity. I know it's a little bit weird, but that's how we write. Radius will be infinity because how far away we going from the center? Oh, very, very far. And far distance or big numbers, we have a symbol, infinity, okay? That's when you getting 0, yes, by the ratio test, remember, radius is infinity and all of the numbers works. That means this function, this power series is convergent for any x value. And I have some solution page. You may pause the video, but we will still talk about this later, about some polynomials and some approximation, but this is that function. Yes, this is this function and works for all of the numbers. Okay, and I just have some quick summary what we did, okay, and that will be everything. Okay, that's we did a couple of exercises, I mean 3 exercises. The second exercise actually was like a finite interval. We checked the endpoints, everything was, yeah. The last exercise, we've got the interval of convergence. We've got from negative infinity to positive infinity, all of the numbers. And actually the first exercise that we did, the power series was just convergent at one point. And we know that that point is center. Could be any number, yes, but it has to be center. Okay. And this is just like the same thing, yes, the power series can only have these 3 possibilities with respect to the interval and the radius. Yeah? Could interval, let's say interval, because it could be convergent at the center only, could be convergent for all of the numbers, or could be convergent. We've got this, yeah? We will solve the inequality and we will have a finite like interval. That means only 3 options. And that's actually the endpoints options. That means this is the interval of convergence, center, going away r to the left, to the right, to the left, and we will have a plus r, the radius. Yeah, that in that inequality we remember from the ratio test will provide us. That means this is the interval, but what we have to remember, the endpoints. We have to test them. That means that's also for the endpoints the only 4 options, both excluded, both included, or maybe 1 each. Open, closed, closed, open. Okay, we did this. And this is the just one more time, the summary, and this will be our last slide. And after this, you can enjoy radius of convergence and interval of convergence. That means summarize one more time. We did one more example. We did the first one, the geometric one. But we remember, we know everything. If you will actually use every power series, when you will use the geometric series, we don't have to test the endpoints because we know that's different. We didn't really use the ratio test. That means this is different. We know that the common ratio must be between -1 and 1, and whatever is the common ratio, we will end up with the interval. Yeah? And then example 1, 2, and 3. The common ratio gave us infinity. The limit was infinity. Then none of the numbers works except 1. The center 0. This one was a typical inequality. The final answer was less than 1. We've got radius 1 interval. And then for this example, by the ratio test, we actually received 0. That limit, a sub n plus 1 over a sub n at infinity gets 0. When we will get 0, all of the values of x works for convergence. That means interval of convergence is from negative infinity to positive infinity. I will really recommend one more time looking at example, all of them, example 0, example 1, 2, and 3. Please redo them. Then you will be so confident with the radius and interval. And of course, solving additional homework assignments. Okay, thank you for your time and enjoy this concept. Thank you.